Um, all right, so what are the different types of energy? We kind of talked about this briefly. I want to make sure we just at least make a list. What are the different types of energy? We just talked about one. Thermal, okay. So write this down here. Thermal energy, kinetic energy. And I just want to briefly explain them. I don't always do a good job with this. Solar. Our eyes on fire here. I was going to write sailor. Oh, that's weird. Solar. Mechanical. Good. Yeah, you guys remember. Mechanical. Electrical. Running out of room.
You spell you demolish mechanical.
Yeah. Oh, jeez. I did.
It's not English, it's okay.
Help me out here. And that doesn't look right.
And potential.
That's right.
Okay. Some words I just look at them like, what? That can't be right. But it is because I'm just not good with words.
Potential energy.
What's that?
Potential energy.
Good.
Paul said that.
Your ball is sitting back there.
Yeah, he's just saying.
Now, potential, but there's also, so there's another way to say this, chemical potential energy. Chemical potential. So there's potential like a ball that's sitting right here. If I just hold it, it has potential. When I let it go, it moves. That's kinetic. Chemical potential energy is kind of more relevant to this class. We'll talk about that in a second. And then there's only one more that I have. And it's dangerous. Radiation, nuclear energy. Radiation is kind of like solar. Because radiation is coming from the sun. You can also get radiation from nuclear reactors. Nuclear reactions. Fission, fusion. Have you heard those words before? Okay. Alright. Okay. Kinetic and thermal. Kind of the sort of same thing. Thermal energy is created by particles moving around. The faster they move, the warmer they are. The more that the temperature increases. Some of you, when I hand back your labs, which I'll start today in period 9, period 4 tomorrow, when we were doing the burner questions, like which way to turn it, and then big flame, small flame, which one's hotter, some of the way you guys explained heat, you were using temperature almost as if it was measuring, almost like temperature was the energy. So I want to make sure we understand this. Temperature is not a form of energy. What is temperature? It measures it. So I just want to make that really clear. These terms are like what energy is, and it has to do with particles moving around or how particles are moving, where they're from, a nuclear reaction, or the sun, for example. But temperature just measures essentially thermal or kinetic energy. So it just measures it. It'll make more sense when I hand back to the lab and go over it. But anyways, so thermal, due to particles moving. Is there heat coming out of that? Go ahead, Ryan. Put your hand over that. Is it warm?
It's kind of cold.
Oh, alright, well, never mind. But if there was heat coming out, that means there would be more particles moving at a faster speed, velocity, so temperature would increase. Solar. So, photons. Was that you? Someone in here was like, photons. Who was that?
That was fun.
Yeah, what's a photon? Oh. Yeah, a little tiny particle of light. Light, the light coming from the sun, radiation, we can see visible light, but there's other light coming from the sun. What are the other types of light we can't see? Just give me one. UV. Someone give me another one. Besides Paul. Or Stavros. Go ahead.
X-rays.
X-rays. What else?
Wait, what?
X-rays.
You can't see X-rays, can you?
Yeah, we see the
the
photo
sun?
when the doctor like put it.
You're telling me you can see X-rays traveling through the air?
I didn't know
Oh,
there
it
were
travels through the
X-rays
air?
traveling.
Wait,
Yeah.
what? I thought
Where
you
do you
were
think they travel through?
wait.
How was
She's thinking of the picture.
the X-ray
Yeah.
that you look at?
I didn't know there was X.
All right,
X-rays.
okay. I don't know. I get it. Now I get it. I'm sorry. So this thing here, like
Yeah, I
you
thought
get-
they meant like this is your
you, like,
broken
you
leg.
slap it
you
up
know?
on the thing and you can
Yeah,
see like
yeah.
bones. Right. So we call that an X-ray, but it's kind of a
They lied.
it's just a misuse of the term. An X-ray is a form of radiation. It's like a little particle of light we can't see. Yeah, no, that's right. That's good. That's not obvious to everybody, so I sometimes forget that. That what we're looking at, you see the bones or whatever, we call that an X-ray image. So it's the image that's left after X-rays pass through your body, because X-rays don't pass through bone or dense material as well as they do soft tissue, like muscles and stuff like that. You can still see some soft tissue, but anyways, that's down the road. We'll talk more about it. Someone give me one more radiation. Without this form of light, it's a form of light, solar, from the sun. It's also from probably the most important thing in your life.
Rebound.
Microwaves, good. Why is that the most important thing?
Relatable.
What am I inferring here?
You use it a lot.
The
What's
radiation, the
what's the
work.
most important thing in your life?
My microwave.
Ooh.
No,
The
Your
microwave.
phone.
your cell phone, right? Okay, kids like lose their minds.
Oh.
And people like, oh my god, I lost my phone. I'm gonna freak out. I was at the gym a couple weeks ago and I put my phone down somewhere and I couldn't find it and I was like panicking. Now, not because I couldn't check, whatever, Instagram or whatever.
Those things are
right?
expensive.
But not because of the money, just because I guess now that we have that technology, I'm like, my wife can't get a hold of me. What if something happens to my daughter? I was like freaking out. But it's sad how like dependent we are on these things. Anyways, how do they talk to each other? If I send you a text, how does it go right from here to your phone?
Satellite? It's like that machine in Willy Wonka, it like goes into the air, it's a particle and then reforms.
Kinda, yeah, Willy Wonka, yeah. Where does this go when I send a text to somebody?
Yeah.
It uses microwaves. Where's it go?
Cell phone.
Cell towers, right? And then there are satellites involved, so the signals are going all over. It's not literally from like here to here, right? So some people, I don't know, maybe older generations don't get that. Like they think maybe it just goes from one to the other. But anyways, that's microwaves. All right, one more. You can't hear them, but it sounds like you can.
Just a colors. You
The
can't see
name
them,
of
but,
name of this particle of light you can't hear, but it.
Vacuum.
All of them?
A vacuum?
The gas from Morgan.
Radio waves. Okay.
Oh.
Radio. They're big, long waves. You can't hear them though. Okay. They're light. They're forms of light. So I'm spending a lot of time on this conversation because that's really important to understand that what we see from the sun is a little tiny spectrum called visible light. There's way more light we can't see. We call that radiation. So anyways, moving on. Mechanical. What's that? Makes energy that makes something work. All right. And move, but it's like moving parts. So like if you pedal a bike, for example, right? What's electrical?
Wires.
What travels through it?
Electricity.
Electricity. What's electricity made of? Electrons. Good. Now, nuclear is when the nucleus of these elements becomes something different. We'll talk more about that down the road. Actually, I have a speaker coming in this year. He reached out to me. He is a nuclear engineer, perhaps, in the Navy? I forget. But he's going to come in and talk to you guys about this. It should be cool. I don't know, he reached out to me, so I forget. Now, right here in your notes, I want you to do one of these things here. I know I'm kind of going on and on, but this is actually a pretty important conversation. Chemical potential energy. That is the energy stored in chemical bonds. So potential means stored, energy stored, that's an O, in chemical bonds. When we eat food, we are converting that energy. So we're taking, Stavros, what do you got? Green beans, right? Okay, so there's chemical potential energy in the bonds of the green beans. When he eats them, his body digests them, his body converts that energy into these other forms. Not nuclear, but he can move his arms, he can walk, he can think. He's got a certain body temperature, he's got heat So he's got all these different energies, and the food we eat is kind of where a lot of that starts. Remember, I had you write down where does all energy start? Where is it again? The sun. Essentially the sun, and then it's all transferred to us. This is a big one in this class. Chemical potential energy, energy stored in chemical bonds. We get a lot of that from food. All right, so I'm done with that conversation. All right, new notes here. Kinetic molecular theory, and we're gonna show you a video here. Kinetic molecular theory is the title. Write this down, please. And kinetic molecular theory. I'm going to play a video, and you are going to figure out the definition of this. And I think the video covers three parts of it. So, lights, please. All right, got a lot of things open here.
There goes the.
Sure. Cool. Yeah, and you might as well just get the first three, I suppose. Should be good. All right.
No one's paying attention to him jumping because the blinds were more interesting. Because we couldn't have put
Okay
them
with
down
that.
one at a time. We tried to put them both down at the
Yeah,
same
that's
time.
what's happening here.
The attack, kept telling you. The PTSD from the last time.
No, never knows.
Does that make you feel better?
It did,
That
actually.
extra.
Made me feel a lot better.
6 inches.
You know, you didn't complete the task, sorry. All right, what is the definition? You're getting that from this video, and then at least 2 parts to this theory.
Oh, it's good.
Here we go.
Oh, must
Sorry.
watch the video.
Well,
That would be
there's-
cool.
yeah, I thought we were doing kinetic energy.
Not as fun.
This is so much better.
The kinetic molecular theory is the theory that all matter is made up of atoms and molecules that are always moving.
You got that right?
Yes.
Oh.
No.
Yeah,
Oh.
why does she talk so fast? Slow her down. Can you rewind?
Look, these little
They're
water
so
particles
happy.
here.
Do you like subtitles?
Nope.
Yeah.
So this one is inaccurate. The hydrogens need to be up a little bit higher, but that's alright. This one's good now.
They're bouncing.
Yeah.
Yeah.
They go down. See, they went down.
The kinetic molecular theory is the theory that all matter is made up of atoms and molecules that are always moving.
I got it.
Very simply stated, all matter is made up of particles, and those particles are always moving. So another way to say is everything is always moving. That's like a very simple way to say it. Everything is always moving. We've already learned that. Solid particles, they don't really move around. What do?
They
Vibrate. Liquids are flowing, they use the word flow, and then gas particles have the most entropy, meaning disorder, kind of moving very quickly all over the place, depending on how hot it is. The hotter it is, the faster gas particles move. Okay, so there's the definition. Moving on.
These particles hold kinetic energy and move around in random directions. In higher temperatures, the particles have high energy, and in
Higher temperatures, particles have higher energy. Remember, temperature measures the energy. So if a particle gains energy from somewhere and moves faster because of that, the temperature will go up correspondingly, right, directly. So the more kinetic energy a particle has, the faster it moves. However you want to word those notes. I know sometimes, a lot of times I write things down. Sometimes I'm just doing it out loud, so I'll leave it up to you. However you write it, it's fine as long as it makes sense. The more energy they have, the faster they move. That's part of this theory. The opposite is true. The less energy they have, the slower they move. And that's tough. That's tough to show you because we can't see atoms or molecules moving around. I used to have a demonstration with mercury. I think I told you about mercury. Now I kept it for longer than I was supposed to, but I had mercury in a sealed tube, and you can boil it pretty easily. So inside the tube, the mercury would start bubbling and boiling. It's pretty cool. And then on top of the mercury are these plastic beads, like little tiny beads. There's, I don't know, like 100 of them. And as you heated it up, the beads would start bouncing around like crazy. And it's just like you see these particles whizzing around. It was just a good visual to show everybody. The hotter it got, the faster those things bounced around. So it was a good demo for that. I'm trying to show you with videos instead. I also have another animation I can show you, but that's the biggest thing here. If you only remember one thing today, that's the one thing to remember. More energy, particles move faster. Okay.
In low temperatures, the particles have less energy.
So, when do you get hot and sweat?
When you run.
When you move around, okay? So sitting here, you have a certain body temperature. Now, if I told everyone to get up and sprint around the room 30 times, you might start sweating and your body temperature would increase because you are moving. Yes?
What if you're sweating but like you're cold? Like
I mean, you might be sick, right?
No, just like,
Like
if you're
cold
outside
sweats.
like at a cold practice or something.
yeah.
And you're like sweating.
So your body only sweats when the temperature is getting too high and it tries to regulate that temperature by sweating. How does it regulate? How does your body regulate the temperature by sweating?
Your sweat cools.
Why does your sweat cool?
Water's a heat sink, so when you sweat, the water will evaporate and take excess heat.
Yeah, when you sweat, the energy from your body transfers into the sweat, and then when the sweat evaporates, it takes the energy with it. So you're talking about outside, cold practice.
Yeah.
Sometimes if you're inside and you're hot and you're sweating, and then you go outside in cold weather, what happens?
You get really cold.
Do you ever notice what happens? You can see it.
You steam.
Yeah.
Steam right off your head, right off your arms, if you're hot enough, and it's cold enough. So, yeah, so when you're cold, you guys say, okay, I'm sweating, but I don't feel hot. Your body is though, so the internal temperature is increasing. So yeah, it's tougher when you're outside in the cold. You're like, I don't feel hot, but I'm still sweating. I get it, but your body's still warm, so it's trying to get rid of that extra heat. Good question. Yeah, so cold particles move really slow, and they tend to huddle together. Penguins. Penguins in Antarctica. They huddle together. Why? Keep warm. Particles do the same thing. They huddle and they don't move as much when they're cold. Okay, moving on.
The more energy a particle has, the faster it will move. In solids such as ice, the particles hardly move at all and hold a regular pattern because the energy is low and the particles are tightly packed. In liquids such as water, the particles have more energy and the freedom to move around. Liquids have the ability to flow and fill the shape of any container they are put in. In gases like steam, the particles have the most energy. These particles are sparse and move around freely. Gases are usually invisible to the eye and they can be expanded and compressed in different pressures.
So, here, I'll let her finish.
All matter is composed of atoms and molecules that are always moving. The higher the temperature, the more energy these particles have.
She said that 3 times, so it's important to understand the more energy they have, the faster they move, and the higher the temperature will be. I do also want to put this down here. Sorry, where's another one? There it is. So, if particles, let's say in a gas, so let's say we have a gas, so gas particles. If particles, so gas particles, are heated, and in parentheses they gain energy. She said they move faster. Okay, I don't need to write that. You should have already written that. All right. What else do they do?
Don't they move?
They move very fast. Very good. What else do they do? The opposite of penguins.
Stay away from each other.
Yes, they expand. Right. Particles are heated. They will move away from each other.
God bless.
And that means, bless you, they will expand. The opposite is true. If you cool them down, they lose energy. They will huddle together. There's the penguin analogy. All right, so that's the gist of the kinetic molecular theory. It's very simple. But I want to show you this thing again. Okay, now there's 2 things happening in here that I want you that we're going to write down. So just watch for 40 seconds. Watch how they move, and I'm going to ask somebody to explain how they are moving. So be prepared.